Meeting the needs of a circular economy is no easy challenge, and most solutions come with significant trade-offs for cost, quality, and operational complexity. iMFLUX's low constant pressure process offers a solution that not only avoids these trade-offs, it has numerous benefits that will make your operation run more smoothly and improve your bottom line. This new processing works with practically any material, mold, or molding machine, new or existing, hydraulic, electric, or hybrid. iMFLUX's lower molding pressure and unique ability to adapt to changing molding conditions in real time provides the ability to process bioresins, post-consumer, and post-industrial recycle and other renewable materials that are challenging or impractical to run with a traditional molding process. Good day, everyone. I'm Brennan Lafferty, publisher of Sustainable Plastics and Plastics News. I welcome you to Ask the Expert, our new live stream series. With Ask the Expert, this is your chance to engage with professionals to address the current business environment, to discuss best practices, and most importantly, to ask some questions. This week, we discuss the vital topic of plastics recycling and the circular economy. We have 4 live streams scheduled this week dealing with supply chain collaboration, trends in technology, the recyclability of plastics, and reducing energy. Today's topic, reducing energy through low-pressure plastics processing. Our expert today is Mr. Gene Altonen, Chief Technical Officer from iMFLUX. Now, Gene will answer your questions after his presentation. However, you can submit a question at any time. You can email spevents@crane.com, or if you're watching this live stream on Facebook, LinkedIn, or YouTube, simply send your questions through those platforms. With that, I'll turn things over to Gene Altonen, Chief Technical Officer at iMFLUX. Take it away, Gene.
Okay, thanks, Brennan. I appreciate the introduction, and thanks to all those who have logged in to the live stream today. So with that, I think we'll go ahead and get started. We don't have a lot of time. So go ahead and advance the slide. So as we get started, I thought I'd take a moment and just give a little bit of background about iMFLUX and who we are. iMFLUX is a company that grew out of the labs and innovation at Procter & Gamble. And we've actually been in business with a commercial product for about 7 years. However, only in the last couple of years have we gone more broadly to the market and been more open about our product and our efforts. So you may not have heard of us until very recently. iMFLUX is a provider of proprietary processing technology. We'll go into a little bit more depth on that today. The technology relies on a specialized controller that communicates with a new or existing injection molding machine, and enables that machine to process with our proprietary technology when those two systems are in communication. So if we advance to the next slide. So what does the system look like? It really is, it's comprised of really 3 main things. There's a controller and the software that resides on that controller, and that's what communicates with the machine. We have a user interface that can be a separate user interface in many cases. However, it can also be an integrated user interface with the OEM's machine user interface. That is a nice option because it's a much slicker, cleaner kind of an integration, but both are available. And then we have a pressure sensor that we add to the machine nozzle. That pressure sensor is what our system closes the loop on, and it's what controls really our entire process. So if we can advance to the next slide. So there are many advantages with this process. There are operational efficiency advantages. It lends itself to material flexibility and being able to apply materials for applications that traditionally they may not be suited to. There are many quality advantages, both dimensional, but also aesthetic type advantages with the process. We reduce pressure. You can do a lot with that reduced pressure, including running smaller machines as an example, less wear and tear on your equipment and so on. So there are a number of advantages in that space. Lower pressure also allows us to lightweight parts, which we'll talk a little bit more about. And then for the purposes of this conversation today, iMFLUX has many sustainability advantages that we'll go a little deeper on. So if we could advance the slide. So to start with, what's different about iMFLUX in a conventional process? Well, we'll start with a conventional process. The conventional process involves injecting a polymer at very high rates. You're trying to get that material into the mold as quickly as you possibly can, take advantage of the shear thinning properties of polymers. And then once that material is about into the mold and it's about 95% full, you switch over to a packing or holding pressure. That packing and holding pressure is necessary to do a couple things. One, you still got to finish out the last 5% of filling that mold, but also as that hot material is now in a cold mold and it's cooling and it's densifying, you have to offset the shrinkage that's occurring there by forcing more material into the mold so you can completely fill out that final part. And then of course you may have some cooling that comes after those two processes are complete. So key things to point out about this process: it's typically very high pressure, it's typically very high shear, and it's a static process. It's not, you set the process up and then you feed it materials and feed it variation, but it doesn't actually adapt to that variation. It has to be able to run a relatively narrow span of variation to be able to produce a good part. So if we advance to the next slide. So how is iMFLUX different? The first thing to point out is that iMFLUX runs at a much lower pressure. So think in terms of about half the pressure is what's possible with an iMFLUX process. And then you might think, well, if I'm running at lower pressures, then I must be filling the mold more slowly, and you'd be correct in that. Shouldn't my cycle times get longer? And somewhat counterintuitively, the answer to that is actually no, your cycle times get faster. And I'll explain that a little bit in a minute. So if we jump to the next slide, there are kind of two big areas that are important to how this process works. One is that it's a process that packs as it fills, and another is that there can never be any hesitation in the flow front in this process. So let's take those one at a time. So if we go to the next slide. So what do we mean by packs as it fills? What we're doing here with this process is we're filling the mold so slowly that we're actually doing most of the work of cooling and densifying that material, so packing that material as that mold is being filled. And so the frozen fractions of the part are actually much, much thicker than what they would be in a traditional type process. And so when that mold is completely filled, there's very little remaining material in that mold that needs to cool and solidify. So in essence, that part is completely formed and almost ready to come out of the mold at the point that mold is completely filled. So that's what we mean by packs as it fills. There is no separate packing phase. It's all done while the mold is being filled. So if we switch to the next slide. So what do we mean by no hesitation? In this process, we're filling the mold so slowly that we really can never have any hesitation in the flow front. If there was ever any hesitation in the flow front, the material would immediately freeze off in that area, and you wouldn't be able to complete filling of that part. And what we do, or what we like to do to illustrate this point, is if you look at the picture of the part that's on your slide, you'll see there's a very small runner extending from the sprue to the subgate. That runner is actually 3 inches long, and it's about 30 thousandths inch in diameter. And so you can imagine, as I'm filling and packing that part, that test part, if I ever hesitated in that tiny little runner, I would immediately freeze off. Well, we don't freeze off because we never hesitate. And that's true not just in this test part or demonstration part, but it's really true in any part. So regardless of the part complexity, design features and other things, the whole thing that makes iMFLUX work is that we're able to keep this material moving and progressing that flow front everywhere in the mold without hesitation. Okay, so if we go to the next slide. So the other key point, especially for this conversation, when we talk about running recycled materials in particular, iMFLUX is an adaptive process. It's not a static process. So as conditions change in the molding system, iMFLUX, the process changes. And so, as things like material viscosity vary, so if material viscosity increases, then the iMFLUX process, the driving pressure would increase to compensate for that increase in viscosity. As viscosity decreases, iMFLUX would decrease the driving pressure to compensate for that, that reduction in viscosity. So, at all times, iMFLUX is interpreting the resistance that it is seeing in the flow front of that material, and it is adapting to match the conditions needed to fill that mold in essentially the same amount of time. So if we go to the next slide. So why is all this important from a sustainability standpoint? iMFLUX has a many advantages when we talk about sustainability. So when we talk about running recycled materials, as I mentioned, we can run very large viscosity variations and manage those variations and still make a good part without any need for an operator adjustment. So that's that adaptive part of our process. And so we do, to give you an example, we do demonstrations where we'll set up a process. Let's say we set up a process for a 5 MFI material, and then we'll transition. We'll dump, say, a 55 melt material right into the hopper right on top of that 5 melt material, and let the machine or let the iMFLUX system manage through that viscosity shift in real time without any operator adjustment. It's completely automatic, and continuing to make good parts through that entire transition. And so, when you're running a virgin material, a typical virgin material might be plus minus 2 MFI. Here we're plus minus, let's call it 25 MFI, and we're able to run that material just as efficiently as running, a more typical virgin material. So this is important as the industry is challenged with running more recycled materials. iMFLUX is able to do that and do it without operator interactions. Another good example here is we work with a company called AGS Technologies. And what AGS is doing is they're taking raw recycled material, so just the flake. They're not going through the repelletization step, and so they're not able to do things in that step to manage viscosity variation. So, what comes in, they clean it up and so on, but they still have a very variable material that they're running and then need to make a high quality part out of that material. They're using iMFLUX to be able to adapt in real time to the material changes that they see, to be able to reliably make that good part, and again, not have to have someone standing there, babysitting that press to make the good part. And I consider that kind of the acid test of trying to run recycle. It's really a variable feedstock that they're able to make great parts. The second big benefit area is around energy use. And so with iMFLUX, with our lower pressure process, we use less filling energy. So there's less work put into the system when we're filling a part, and so we use less energy to fill that mold. Because we're working at lower pressures, we use less clamping energy. Because we're not clamping to the same tonnage, we don't need as much energy to do that. And then we also run at faster cycles. And when you run at faster cycles, you take all of the base energy of the machine that's needed to, just for the machine to continually operate, and you average that energy over a lot more parts. And so you use less energy on a per part basis. And so when you put all those things together, you actually see energy reductions that are very substantial. They can range from about 10% to as much as about 30% in areas where we've observed the energy reduction. And then lighter parts, as I mentioned earlier, when you run at lower pressures, you can lightweight your part without, making your pressures so high that it becomes impractical. So it's a great lightweighting technology, which is removing material from the waste stream at that point. And then finally, you're getting these advantages, and again, without the trade-offs that are typically, cost, complexity, and quality are generally trade-offs in this space that we're able to give you these benefits without those trade-offs. And so with that overview, I think we're ready to take some questions.
All right, awesome. Thanks, Gene. So for those of you who may have joined us before and didn't hear this at the top, if you want to email some questions to Gene, send them to spevents@crane.com. Or if you're watching the live stream on Facebook, YouTube, or LinkedIn, send the questions through those platforms. All right, Gene, we do have some questions here coming in. The first one, interesting question. Why can't I just run a constant pressure process using my standard machine by simply pressure limiting the process? Something trying to mimic what the iMFLUX technology would do.
Right. So there's really three main reasons that won't work. So the first reason is that to run this process, you really need to be able to control the process by plastic pressure, not a proxy for plastic pressure, like how hard are you pushing on the plastic through, with load cell reading or a hydraulic pressure, but actual plastic pressure. The reason for that is that polymers are compressible. And so how hard I'm pushing on the material at one end of the screw does not translate into what is my actual plastic pressure at the other end of the screw. And that difference is sufficient, large enough to create conditions where your flow front would hesitate downstream in the mold. And as I mentioned earlier, hesitation would mean, an unfilled part or a quality defect. The other big reason that doesn't work very well is that when a standard machine has essentially a set of tuning parameters in terms of how aggressively or unaggressively the machine operates, and each machine is set with really static tuning parameters. And with iMFLUX, we actually have dynamic tuning parameters. So when we put a new mold, a new material for a new part into a mold, the system actually tunes the performance of the machine to match the needs of that part and system. And by doing that, the responsiveness of the machine in terms of what's required for that part are substantially improved, again, giving us much better control and no hesitation. And then finally, it's critically important that the process is able to adapt in real time to viscosity variations. So, materials vary. And when those materials vary, if your system isn't able to detect that and understand it and adapt to it, you'll wind up with flash and short shots on a continual basis.
Okay. All right. Well, that makes a lot of sense. Not recommended.
Not recommended.
Okay. All right, Gene, a question from our YouTube audience. How how would this react with a fractional melt resin? What are the resin limitations or type of resin limitations?
So when we talk about running a fractional melt material, it's a great application for iMFLUX, because what we're doing is we're running at lower pressures. And when you run at lower pressures, you provide some headspace in an application for those pressures to be increased while still being able to run a given part. And so the problem with fractional melts are typically your injection pressures are just so high to get that material into the mold, it's just impractical. With iMFLUX, if you start from a base of about 50% of the pressure, you've created the possibility of running that fractional melt material into many more applications. Mm-hmm. So we have done a little bit of that work, and it works extremely well.
Oh, wonderful. Okay. Another YouTube question about mold changes. Are there any mold changes required to accommodate iMFLUX?
So this is kind of a two-part answer. The first part is most of the work we do is in an existing mold. So when we talk about the advantages of iMFLUX, we're really talking an apples to apples, same mold to same mold. You get get these cycle time advantages, the OEE advantages, and so on. There's no need to modify the mold. We don't add any sensors to the mold. We just run the mold as is, okay, and get these benefits. Now, the second part to the question is, when you're designing a new mold, there are opportunities to really take advantage of the iMFLUX technology to get even more benefits. So, trying to fit more cavities in the mold, as an example, because we're running at lower pressures, you can upcavitate a mold, still run in the same size press, as an example. Mm-hmm. You can mold things thin to thick, and some other design considerations, that many designs can benefit from. So if you are designing a new mold, it's always a good idea to think about having iMFLUX in that process right from the beginning and try to maximize the advantages all the way through.
Okay. All right. A question from email. Can you process PHA? Have you tried this technology with PHA that is processed at a maximum temperature of 130 degrees Celsius? Using conventional injection molding techniques, we can't get the mold to fill.
Yeah. So I think that specific example, I'm not sure if we've done a PHA example, particularly one where we couldn't fill. What I would tell you is, if your limitations on being able to fill the mold are pressure, it's very likely that you're going to see some big improvements when you use iMFLUX. If you're starting from half the pressure, if its pressure is what you need, then that's definitely, you're going to see some advantages from that. I'll also say that that depending on the issues you're experiencing, iMFLUX fills, it essentially flows into the mold perfectly laminarly, and it doesn't have it has no hesitation anywhere as it's flowing into the mold, and that sometimes can be beneficial to a lot of different materials and part types, because you're able to keep that material moving everywhere in the mold, where in a conventional process you may have areas where it's stalling. Let's say you're flowing past a rib, and you flow right past that rib until that nominal wall fills out, and then you come back and backfill that rib. That's in a conventional process. Yeah. That doesn't happen in an iMFLUX process. You will reach that rib and you'll progress down that rib while you continue to progress down the nominal wall.
Okay. So to the viewer who asked that question, we're going to have Gene's contact information up at the end if you have a follow-up question about PHA. But Gene, that makes me wonder, because this question, I can tell from the spelling, for example, that this is not a US-based question. Is the iMFLUX technology available worldwide, or is it just in certain parts of the world?
Yeah. So we are dominantly in North America, we'll say, or in maybe Latin America. We're very broadly available here. We are creating a lot greater availability in Europe. and that part of our business has been growing pretty steadily. And today we are in Asia with partners. So if you think about, many of our customers are multinationals.
Yeah.
And we're there with those customers. And so, we look, when we talk about going to Asia, the conditions really need to be right for us to go, because we don't have an organization on the ground there.
Yeah.
But we absolutely will look at and consider opportunities to go to Asia.
Okay, very good. Now a more general question, if that was more specific, where does the technology work best? Where does the technology not work?
Mm-hmm. So the technology works extremely well, when you have things like, materials that are highly variable and difficult to manage. This is going to be a great choice for you. Where you have, materials that are prone to aesthetic defects, maybe it's ghosting, or maybe it's tiger striping, or, many different cosmetic defects. Because of the way this, our process flows into the mold, you're going to see big advantages there. Optical applications, big advantages. Filled materials can often see big advantages here. So, those are all really good choices, but there's lots of good choices. Maybe an overriding, statement there on where does it work best. We haven't really found places where it doesn't work better than the conventional process, but the range of that benefit may vary a little bit from one application to another. The where does it not work? The places where it doesn't work are generally related to things like this. In the case of a velocity limited press, as an example, when we have a velocity limited press, what that does is it won't allow us to reach our pressure set point. So, we ask for the press to give us the maximum that it can give us, but when it gives us that maximum, it can't build to that pressure set point that we're after fast enough. And so you really don't get an influx process that way. So you don't see a lot of benefit. When another scenario would be like a recovery limited scenario where, we're packing as we're filling, we don't need as much cooling time. We want to take cooling time out of a process. So if we had an application where, let's say we wanted to take 5 seconds of cooling out of the process, but the process became recovery limited at that point, and we can only take, say, 1 second out of the process, we're leaving 4 seconds on the table in that scenario. So we don't see as big a benefit there as well.
Okay. So Gene, you said you got multinational partners for this process. Can you talk a little bit about what are some of the end markets or companies, OEMs, that are using the iMFLUX technology?
Mm-hmm. Yeah, so we have customers that range across a variety of industries. Of course, our parent company, Procter & Gamble, is a multinational in really in every region of the world, and those products would mainly be consumer products, packaging, also blades and razors, oral care, toothbrushes, and so on. Then we have other partners that are into consumer electronics. In that space, we have customers that are into storage containers and waste containers and those kind of markets. So we're really all over the map, and it's a little bit of an offshoot of when we were vetting the technology, dial back 7 or 8 years ago. We really wanted to understand how well this technology worked across a variety of applications. So we took it into all those applications early, and so we're really working. I mean, large appliances, small appliances, automotive components. I mean, it's really just about every industry at this point.
Yeah, it sure sounds like it. Okay, that's helpful. So back to the specifics. Does the process work with specialty molding formats such as 2-shot, in-mold labeling, gas assist, etc.?
Yeah. So the system is capable of running. It's designed to run. A standard box is designed to run up to 4 injection units. So if you had an application where you were running 2 shots, 3 shots, or 4 shots, that that's a standard offering from our platform. We can do more, but our standard platform is up to 4. We've done a fair amount of work in the co-injection space, and the technology works extremely well for co-injection because you're controlling both materials by pressure. And because you're controlling both of the materials by pressure, you don't have the traditional problems of the inner layer trying to force through the outer layer or the outer layer trying to pinch off the inner layer. You're able to control those much more easily and precisely in this scenario. And similarly with things like gas assist, it's another great example of, it's a great marriage of technology with gas assist because we're able to form such a thicker and more uniform frozen fraction of material against the mold. It's much easier to control that gas void inside the part as a result of that. And it also helps with controlling the leading and trailing edge, so getting the bubble where you want it. In-mold labeling, also great application because, again, we're filling slower with nearly perfect laminar flow. It works extremely well with in-mold labeling.
Awesome. Well, I'm afraid our time is run short. Gene, any final thoughts for the viewers out there watching about iMFLUX?
Yeah, I mean, I think that when it comes to sustainable technologies, the world is looking for solutions for how do we solve for the circular economy? How do we run these crazy recycled materials that everybody wants us to run and they're tough to run? iMFLUX has really a range of benefits. It's going to make those materials super easy to run. It's going to do it with lower energy use, and it's going to help you design lighter parts. And so, it's kind of hitting on all signals, all areas from a recycle standpoint. And most importantly, it's doing it without the trade-offs that a lot of technologies have in trying to run particularly recycled material. And you get these other benefits as well. So you're going to still get the operational efficiency benefits, the quality benefits, and the other things. So it's really a very, very attractive solution for running sustainable materials in a circular economy.
Yeah, it sure seems like it. Well, Gene, great to see you again. I know it's been a while since we've been able to be in the same place, but thanks for your insight today. For those of you watching, if you want to reach out to Gene, email him at the address you're seeing on your screen. I know he would love to talk to you about iMFLUX. So again, my thanks again today to our expert, Gene Altonen from iMFLUX. My thanks to you for joining us for Ask the Expert. We hope you enjoyed our entire series on plastics recycling and the circular economy. To view the other live streams from earlier this week, visit sustainableplastics.com/ask-expert. Our next Ask the Expert series is the week of August 10th. The topic, improving operations. Until then, have a great day. I'm Brennan Lafferty. Thanks for watching Ask the Expert with Sustainable Plastics and Plastics News. Now stay tuned for a parting message from iMFLUX. iMFLUX, innovators transforming the future of plastic injection molding. iMFLUX is the only molding company that integrates game-changing processing software and machine learning with a mold building and innovation center. They provide the way to autonomous molding with a new capability to design and mold that impossible part. The revolutionary low constant pressure injection molding platform works on virtually any machine, any material, any mold. With iMFLUX, your sites run more reliably with fewer operator adjustments. You'll produce higher quality parts, reduce costs, and lower capital, all while advancing your sustainability efforts. For more information, visit imflux.com or email info@imflux.com.